Or let's suppose that your incoming thing is light and your mystery target is an electron. This is actually how we prove that light behaves like a particle. Because if light were a wave, if it were an electromagnetic wave, then the electron would oscillate in the direction of the electric field and produce more radiation in every direction at the exact same frequency and wavelength as the incoming light. And for the most part, that does happen. But there's also evidence that there are some angles at which that wavelength of the light seems to shift a bit. And we can actually model that if we model light instead of as a wave, as a particle. And then model this as a collision. Well, you know about collisions, right? They're governed by conservation of momentum and by conservation of energy. Let's take a look at the momentum condition first, right? So this light particle is going to have one momentum coming in here. In order for the model to work, we're going to relate the light's momentum to its wavelength, h over lambda, where h is Planck's constant. The electron is not going to have any momentum at first, so we're going to consider it to be at rest. After the collision, the photon, the light particle, is going to bounce off this way with a new momentum of h over lambda prime. We're going to have lambda prime is our new momentum. The prime means after the collision, lambda prime is the new wavelength, p prime is the new momentum. And our electron will have a momentum coming off this way. We'll just call it PE since we're not particularly interested in its value. These things are vectors, so we'll need to distinguish this thing's angle. Let's call that angle phi, and this thing will give an angle, let's call that theta. Again, this thing is a vector, so we'll need to think about the x components here. So this thing obviously has just an x component here since it's going horizontally. We got h over lambda going to equal this thing's x component. That will get the cosine of phi. So we'll have an h over lambda prime cosine phi plus the momentum of the electron times cosine of theta. And then we've got to use the y component as well. This thing has 0 y component. And so that gives us h over lambda prime times the sine of phi minus PE sine of theta. Since it's going in the opposite direction, we need those two things to cancel. The conservation of energy gets pretty interesting. The energy for a photon here is going to be hc over lambda. Plus, since we're working near the speed of light, we need some relativity. So we're going to use the mass of the electron times c squared. Right, yeah. Going to equal our new energy over here, hc over lambda prime, plus the total energy of the electron. We'll work on what that is in a little bit because now it has its mass energy and its kinetic energy. Always start with the simplest looking equation, the one with the 0 in it. This y component of conservation of momentum is going to allow me to eliminate sine of theta, which I can relate to cosine of theta up here. So that's just going to tell me that sine of theta is going to be h sine phi divided by lambda prime sine theta divided by lambda prime PE. I can also take this equation and solve it for cosine theta. So my cosine theta, first we'll subtract this over to the other side. So I'll have an h over lambda minus an h cosine phi over lambda prime. And then I'm going to take that whole thing. So I've taken this subtract over here. I can divide that whole thing by PE. So I'll take this whole thing and divide by PE. The reason that's useful, anytime you have a sine of something you don't care about and a cosine of something you don't care about, I can square this and square this to get 1. Right? So best trig identity in the world is cosine square theta plus sine square theta equals 1. So I can take this thing and square it. So I'll have an h over lambda minus an h cosine phi over lambda prime. Take that and square it. Divide by a PE squared plus the sine squared. Make this an h squared sine square phi over lambda prime squared PE squared. Going to equal 1. Well, that's useful because I can use that to get PE over here, right? I have a PE in the denominator, PE in the denominator. I can just multiply both sides by PE squared. So I'll have the momentum of the electron squared equals all of this stuff added together. That's going to be useful in our last equation over here. That's going to be useful in our last equation over here because this energy of the electron is going to equal PE squared C squared plus ME squared C to the fourth, all square rooted. That just comes from special theory of relativity. Uh-oh, I'm getting a severe glare there. Let's fix that. I think that's recent. I suppose I could just put that. Oh, gosh, that looks bad. All right, hold on. Use the tools that you have. All right. I can fix that. Maybe. And I have this PE squared in here, so I'm going to get to combine those two. Let's work on this equation for a little bit. I can move this HC over lambda prime over here. So I'll have an HC, a 1 over lambda minus 1 over lambda prime plus MEC squared going to equal this thing over here, this square root of PE squared C squared plus ME squared C to the fourth. I'd rather not have this square root over here, so we'll square both sides. So we'll have a HC 1 over lambda minus 1 over lambda prime plus MEC squared. Going to equal this whole thing. Square that. Going to equal this whole thing without the square root. Let's go ahead and replace our PE squared over here. So we'll have an H over lambda minus H cosine phi over lambda prime squared plus H squared sine square phi over lambda prime squared. That whole thing is PE squared. So this gets multiplied by a C squared, and this gets multiplied by a C squared, plus harmless little ME squared C to the fourth over here. This is now all the information that I need in order to get something I can use in an experiment, because I have my incoming wavelength, my outgoing wavelength, and my scattering angle phi. We're just looking for a bunch of other stuff to cancel. So we'll take this thing, we'll FOIL it, so I'll have the first thing squared, H squared C squared, 1 over lambda minus 1 over lambda prime squared, plus last thing squared, ME squared C to the fourth, plus 2 times the cross term, the first term times the second term. So we'll have an HC 1 over lambda minus 1 over lambda prime MEC squared, going to equal everything from the right hand side. Let's go ahead and FOIL this out as well. So I'll have an H squared over lambda squared plus the next term H squared cosine squared phi over lambda prime squared minus 2 times the combination H squared cosine phi over lambda prime plus this thing, all of that times a C squared, C squared, C squared, C squared, there we go, plus this thing, H squared, C squared, sine square phi over lambda prime squared, plus this guy still hanging on, ME squared C to the fourth. All right. Remember, algebra always has to get worse before it gets better. What I can see here right away is I've got an ME squared C to the fourth, ME squared C to the fourth. Those will go away. This is already looking better. Now it's time to start thinking about these sine squares and cosine squares. Remember, cosine squared of a thing plus sine squared of a thing always equals 1. Well, here I've got a cosine squared phi. Here I've got a sine squared phi. And they're being multiplied by all the same stuff. H squared C squared over lambda prime squared, H squared C squared over lambda prime squared. So my right-hand side is going to get those two to combine. Is there anybody else I might be able to cancel between the two sides? I think I will get 2. My left-hand side if I FOIL this out, I'll have an h squared c squared times 1 over lambda squared plus 1 over lambda prime squared minus 2 over lambda lambda prime. A lot of foiling going on here. Aren't you glad you practiced that? Plus 2 h bar mec cubed. You don't see a c cubed all that often. 1 over lambda minus 1 over lambda prime. Going to equal my right-hand side now. I've got a c squared h squared over lambda squared plus these two things added together will just give me a c squared h squared over lambda prime squared minus a 2c squared h squared cosine phi over lambda lambda prime. Let's find some other things that might cancel for us. I've got an h squared c squared over lambda squared, h squared c squared over lambda squared, so this term and this term go away. Same thing here with a lambda prime squared in the denominator. That's nice. What else is going to go away? In the folks that are left, I can start canceling some constants. So everybody who's left has a c squared in them. So this is c squared, this is c squared, this is c cubed, so that'll just become c. Everybody has at least one h, so that h goes away, that h goes away, that h goes away. And so what I'm left with and everybody has a 2, so you've got a 2, you've got a 2, you've got a 2. Anything anybody has in common must go. Let's see, so on the left-hand side, I'll have a negative h over lambda lambda prime, negative h lambda lambda prime, plus an mec 1 over lambda minus 1 over lambda prime. Good. Going to equal an h cosine phi over lambda lambda prime. It is a bit awkward having all of these lambdas and lambda primes in the denominator, so we are going to take everybody and multiply everybody by lambda lambda prime. That will get rid of this, that'll get rid of this, and that'll turn this, instead of 1 over lambda, it'll turn this lambda and this lambda will cancel. That will give me a lambda prime. This lambda prime cancel. That will give me a lambda. Hooray. So I will have here a negative h plus mec lambda prime minus lambda, going to equal an h cosine phi. So if I want to think of this in terms of the change in lambda, right? Change in lambda, meaning my final one minus my initial one. How much does the wavelength change by? I'll get an h. I am missing, I missed a minus sign on this guy. Thank you. That's going to be a 1 minus cosine phi times this, take this mec, put it in the denominator. This is what you would expect to get if light is behaving like a particle instead of a wave. Instead of getting a constant wavelength out everywhere, you expect the wavelength to change based on the angle that you look at. And that's actually what we see in experiment. So that's how we confirm that light is a particle. Here we're actually going to take a look at two activities to look at these two types of scattering that I mentioned. In this first one, we are going to be oscillating an electron up and down. What you'll see is that you have this electromagnetic wave, this light wave coming in, and then you have electric field coming out. And so whatever frequency is coming in, the electron's going to oscillate at, and that's the same frequency that the light wave is going to oscillate at. Now this is fun to watch, but it's difficult to get quantitatively. So what I've done down here is I've set up a couple of detectors, and we're going to see the electric field pattern at those detectors. So right now this is at 0 degrees. What I can do is click and drag to move the slider to move the purple detector. So I have a blue detector at 0. That's going to be my reference point. That's going to stay at 0. Here, the purple one, I'm going to move around like I would do in an experiment to see what kind of electric field pattern I get out. And you can see I get out a little bit different pattern. It's different in terms of the amplitude, right? The purple one has a higher amplitude that oscillates, but the blue one is consistent, but it's lower. I can move this thing around. I get something very different
for the purple now. Let's see, how far can I move this thing around? I think I can move it all the way to, okay, move it all the way 80 degrees, a little bit off screen. There we go. So I'm at 80 degrees, almost perpendicular to it. I get something, again, very different for the purple. I can even move it back down the other way. It should be symmetric. If I go from positive 80 to negative 80, yeah, it should be the same pattern because there's not really anything special about that direction. But the thing that's important, right, this pattern's really cool, but the thing that's really important to notice is that it's always the same frequency, right? So the blue is obviously going to be the same because it's not moving, but no matter where I move the purple detector to, I always get the same frequency, right? These peaks are always pretty much on top of each other. I'm getting the same frequency out. So classically, we expect whatever the oscillation frequency is coming in, that's the oscillation frequency that should come out. Then we come over to the Compton model, to the quantum model. So here what we're doing, we're modeling an elastic collision. Let's now take a look at a simulation of classical light interacting with a non-relativistic electron. So we've got a light wave coming in here. It's being modeled as the electric field oscillating up and down, so the magnetic field is oscillating in and out of the screen. The electric field is causing the electron to accelerate up and down because it's experiencing this changing field. It experiences a changing force. It will accelerate it in the upward direction and then the downward direction, gives you this nice sinusoidal motion. One of the outcomes of classical electrodynamics is that an accelerating charge produces electromagnetic radiation. The math behind it is rather complicated, as we'll see in the code, but in this case it produces this really neat pattern where the field is kind of doing this curve around the electron there. It's oscillating both in direction and in amplitude, which is pretty cool. And if you place a detector here at the purple dot, you get out this radiation pattern. So this is what the electromagnetic radiation is going to look like a little bit far away from the electron. You notice it's oscillating. If you look closely, it's oscillating with the same frequency as the incoming light. And in fact, that's going to be true no matter where you place this detector. So for example, I can click and drag the slider to move the purple detector around. I've left behind a blue detector so that we can have the same pattern there for reference. So the blue pattern is always going to be the same. It's always going to be at this 0 degrees. Here I've moved this up about 18 degrees. And you see I get a slightly different pattern. I get a higher peak, so there's a little bit more amplitude coming out at 18 degrees than there is at 0 degrees. And in fact, that amplitude itself oscillates. It's got a higher, it's got a lower, it's got a higher, it's got a lower, it's got a little bit of a hiccup to it. But what I want you to notice is that it oscillates with the same frequency. Even though it's got this new pattern to it, it's still oscillating with the same frequency as before. So if you sit at the blue detector or if you sit at the purple detector, you're going to see the same color light as came into the electron. And in fact, you get this no matter where you place this detector. I could rotate it up to, let's say, 43 degrees here. Again, I get this little hiccup to the oscillation pattern, but it's the same frequency. And you can probably imagine I'll do that even if I go down to negative 43, or how about 45? There we go. We like 45 degrees usually. So come down here to 45 degrees. Again, a hiccup pattern to the oscillation, but again, it's with the same frequency. The way we're doing this, there's a lot of setup to this code to create the visualization, but basically we're setting up the wavelength of the incoming light. We're then setting up its wave vector to point to the right. We create our electron. The electron's going to be located at the center of the screen initially. We give it a velocity, a charge, a mass. Then here what we're doing is we're calculating the electric field coming in. This is going to be a function of time. So it's this wave pattern that's got k dot the position minus omega t. That's what produces that nice plane wave coming in that we saw. Then here we're calculating what the electric field is that the accelerating electron creates. This is the part that's a little bit complicated. It involves the electron's velocity. It involves the separation vector between where the electron is and where you're going to be looking for the outcoming field. It has this modified velocity that is the speed of light times the separation vector, unit vector. I will leave for you in the description below a link to a reference about this because it has this really great derivation that takes pages and pages of text to accomplish, but this is the electric field of an accelerating charge. Then what we're going to do in the animation loop, so here we're just setting up all the detectors, etc. Here in the animation loop, what we're doing is calculating the force on the electron, so that's going to be the charge times the field. I've added in a tiny damping force here just to keep the system stable. If you don't include this, that electron is going to creep up in terms of its energy and it's eventually going to leave the screen. So we have just a tiny damping force just to keep the system stable. Here we update the electron's velocity. The way you do that is basically by rearranging the force equation. So you've learned in Physics 1 that force equals mass times delta V over delta T. And so what we're doing to get this equation is we're rearranging it for delta V to be equal to the force divided by the mass times a small step forward in time. This delta T is how much time there is between frames in the animation. And so what we're doing is we're adding to the velocity this small change in velocity. And we do the same thing for the position. We add to the position the electron's velocity times dt. Finally, we just use that electric field that electric field of an accelerating charge to create those output vectors so you can visualize it and to calculate the magnitude of the field here at each of our detector locations. So that's where this simulation comes from. You could also change the wavelength. Let's suppose I want to make this a broader wave. Control 2 to run. You notice I've got a much longer wave this time with much lower frequency. Oh, and I've got field vectors coming out of the screen there. I probably need to change my scale factor there. But again, you notice no matter where you place your detectors, you're going to get the same frequency as you had coming in. Oh my, we got quite a lot of electric field there. I think I need to increase my damping force there. Why don't we try that? Where's the damping force? Here it is. Maybe I need to change this. Let's increase it by a factor of 5. Yeah, still getting some amazing electric field vectors there. The important thing is what we're seeing at the detector, though. Let's say we move it to just 15 degrees. Again, the amplitudes are different, but we're going to get the same frequency as we had coming in. Now let's compare that with the quantum system. You notice we're setting up the same information at the beginning. We have a wavelength, we have a frequency, we have the speed of light, but we're going to be using that information differently now because now instead of creating a wave coming in, we're going to create a photon. A photon is going to be a sphere instead of a wave pattern, and we're going to model its collision with the electron. We're still going to set up our detectors here. So we're going to have our stationary detector and our moving detector. They're going to follow the same principles that we had before in terms of we're going to be able to move them around. Come down to the animation loop and things are a little bit different. This time, instead of calculating a force between the two, we're going to check for a collision. So initially we have not collided, so we're looking for when a collision is going to take place. The way you check for a collision is you just check for whether the two shapes have overlapped. So if the difference in their position vectors is less than the center-to-center distance you would expect when they're just barely touching each other. So in order to get this, we need to calculate our change in lambda. This is our 1 minus cosine of the angle here. That's that 1 minus cosine phi that we had. We're going to change our wavelength by that amount. So we had an incoming wavelength. Now we have an outgoing wavelength. And then we're going to modify the photon's color, right? So wavelength corresponds to light's color. So we're going to paint the photon a different color depending on where we're looking at in the outcoming angle. We're also going to change the photon's velocity to go along that angle because this is the direction we're looking at now. And basically when the photon reaches the right-hand edge of the screen, we're going to reset the photon, put it back at the beginning so we can repeat this experiment. So now what you imagine, instead of having a wave over here, we now have a particle coming in. We have a photon coming in. Initially, we're looking at 0 degrees. We get no wavelength change at 0 degrees. So if the photon manages to just graze the electron, to not really hit it, right? Imagine it's just barely going above it. Then it's not going to have any change in wavelength. It's going to be like it never met the photon, or the it's going to be like it never met the electron to begin with. However, once I start moving the detector up, let's say I move the detector up to 23 degrees, now my photon's going to scatter off this way. So the way you have to imagine this is that you have many, many photons coming in, and we just happen to be seeing the one that is scattering off at this angle. There's still photons scattering off in these other directions, but for the sake of computational simplicity, we're just going to render one at a time. So just imagine there's other photons coming in that we don't see because they're not coming out at this angle. I don't have too much of a change in the color right now, right? This mostly happens at very large backscattering angles. So let's increase this. Let's go up to maybe 45 degrees. Still not getting a huge change in the color there. Let's go up to 60-something degrees. Okay, it's getting a little bit dimmer. You notice it's changing color ever so slightly. It's getting a little bit less blue there. Let's go up to 90. Okay, now I can definitely see a change in the colors, going from blue to this brownish color. This isn't the actual color that the light would be. This is just rendering it in RGB. Let's see if we can get exactly 90 here. If I use my keyboard keys. There we go. Let's get that to exactly 90. Yeah, it's turning a little bit differently here. So there's some critical point over here where it starts to become noticeable. Yeah, there it's getting a little bit dimmer. Let's go down to maybe 60 something. Yeah, so you can see if you were to do this enough times, you would be able to see what the change there looks like. Let's go to a backscattered angle over here. Let's suppose it bounces off and bounces back the other way. There I'm definitely getting a change. We're going from bluish to reddish. Do I have this set to go all the way to 180? I do have it set to go all the way to 180. Let's suppose the photon bounces back exactly. There it's got the most extreme change. It's going to change from blue to red. Now it looks like it's pinging back and forth. Remember, that's a new photon every time. It's not really bouncing off the detector there. You'll get the same pattern if you come down to negative because cosine is an even function. So going negative is going to give you the same pattern as if you went in the positive direction. So anyway, this change in wavelength, this is one of the main proofs that we have, or main demonstrations that we have, that light behaves like a particle instead of like a wave. You still get the same frequency coming out when you're looking in the forward direction, right? That really doesn't change it that much. It's at these significantly deviated angles that you get a really noticeable change in the wavelength.